Welcome to Talkcast and to Chapter 9 of The Fabric of Reality, Part 1 of my discussion about quantum computers, as the chapter is called. As with many of David Deutsch's chapters in his two books, this chapter, perhaps more than any other, could be turned into an entire book on its own. It's about quantum computers, yes, but it's also about the history of computation more broadly. It's also about areas of mathematics, about quantum cryptography, and how it is that we come to know about the world, and the tension between quantum physics and classical physics. All of this comes to bear on the contents of this chapter, and so it's why I say this could easily be a book all on its own. In fact, having read a lot of popular science myself over the years, I would say that this chapter has more substance than many of the popular science books out there on similar topics. Quantum computation, as I've observed here on Talkcast before, is a multi-billion-dollar multinational industry now. People and nations are racing to construct the first universal quantum computer, the computer that could do anything that any other quantum computer can do. At the moment, we only have special-purpose quantum computers, but there are dozens, perhaps more than that, perhaps hundreds, of research institutes, militaries, universities, all engaged in trying to improve quantum computing technology, especially the hardware of quantum computer technology, but many of them were working on quantum algorithms, the software as well, that would run on these computers that would enable us to do faster computations for certain tasks. There are a variety of hardware approaches to this problem of how do you make a good quantum computer? How do you improve the quantum computer architecture? I'm going to avoid talking about the different approaches. I've mentioned these in my series on the beginning of infinity, and in fact, one of the experiments that David Deutsch mentions in this chapter, Chapter 9 of The Fabric of Reality, is something that I talk about at length in the multiverse chapter of the beginning of infinity. So although in this chapter we'll see there is a lot of double up between what I've talked about on previous episodes of Talkcast and this chapter here, I'm still going to take this chapter in two parts. The first part is more contextual, about, I suppose, setting the scene for what the problem is that quantum computers are going to solve. And in the second half, we'll talk a little bit more about the inner workings in principle from a God's eye perspective, so to speak, from a high-level abstract perspective of how these things would work in general. Quantum computing is an exciting, emergent field. Perhaps it's moved a little more slowly than some of the pioneers of the field expected it to move, but it is making progress. And it offers the exciting new possibility of a new way of computing stuff and solving problems that hitherto were intractable for other kinds of computers, namely the classical computers that we have. In particular, quantum computers can efficiently simulate quantum systems like atoms and molecules and, well, in principle, anything, because everything is quantum ultimately, aside from gravity so far as we know. But there are mathematical problems and scientific problems that could benefit from a fully functioning universal quantum computer. So let's get into the chapter and to see what David said some 25 years ago now on the subject, but which is as relevant today as it ever was, because these are universal claims about a universal truth about the world. So here we are, Chapter 9, Quantum Computers, and David writes, quote, "To anyone new to the subject, quantum computation sounds like the name of a new technology, the latest perhaps in a remarkable succession that has included mechanical computation, transistorized electronic computation, silicon chip computation, and so on. And it is true that even existing computer technology relies on microscopic quantum mechanical processes. Of course, all physical processes are quantum mechanical, but here I mean ones for which classical physics, i.e. non-quantum physics, gives very inaccurate predictions. If the trend towards ever faster, more compact computer hardware is to continue, the technology must become even more quantum mechanical in this sense, simply because quantum mechanical effects are dominant in all sufficiently small systems." End quote. Okay, so my reflection on that. So the issue is this. Classical computers consist of circuitry, and the circuitry transmits electrons from one place to another to perform the mechanical task of computation. Now, electrons in one place represent memory being stored. Electrons moving in this place represent some sort of computation being performed. And well, if you want things to move faster, then you pack more of all of that into a smaller space, among other things. So if you're packing your circuitry into a smaller space, eventually the wiring effectively gets closer and closer together. And if you've got electrons going this way and electrons whizzing that way, well, you don't want them to cross over. If they cross over, it's like a car collision. You want the traffic to be moving nice and parallel, and never the twain shall meet. But if electrons do get closer and closer together, then they're going to have effects on one another. And those effects are going to be quantum effects, among other things. Or if you have a circuit without electrons, and one with electrons, maybe these electrons that are travelling down this road, effectively, this wire, are going to jump over to a place where you don't want them to go. At the moment, that is not so much of a problem because everything's being kept far enough apart. But as the transistors get smaller, these effects become more noticeable. And this could have an effect on Moore's law, the idea that about every 18 months, the power of a computer or the speed of a computer doubles. It used to be the case that it was thought that the clock speed of the processor would get faster and faster and faster, and that this eventually would reach a limit. But, well, they're doing all sorts of weird, funny, clever engineering right now and just having multiple cores on your processor. So the processors are indeed continuing to get more powerful without necessarily getting faster per processor. So Moore's law is still holding. But the majority of engineers and scientists working in the field tend to think there's a wall ahead of us. And that wall ahead of us is the boundary between classical computation and quantum computation. If you want to continue to get faster beyond the wall, you have to become a quantum computer. A classical computer just can't get, the circuitry just can't continue to get ever smaller. The clock speeds can't continue to get ever faster. There must be a limit imposed by simple physics. This genuinely is one of those areas where the great dichotomy rears its head. Either a thing is prohibited by the laws of physics or it was possible given the right knowledge. Now, hitherto, increasing the speed and power of a classical computer is possible. We just had to create the right knowledge. But we get to a point where, well, the laws of physics place a prohibition on how close two electrons can be before they start interacting in quantum ways with one another, before they start interfering, let's say. And either that can be a problem for your classical computer, or it can be an effect to take advantage of. And let's keep on going. David writes, all present-day computers, whatever quantum mechanical processes they may exploit, are merely different technological implementations of the same classical idea, that of the universal Turing machine. That is why the repertoire of computations available to all existing computers is essentially the same. They differ only in their speed, memory capacity, and input-output devices. That is to say, even the lowliest of today's home computers can be programmed to solve any problem or render any environment that our most powerful computers can, provided only that it is given additional memory, allowed to run for long enough, and given appropriate hardware for displaying its results. End quote. So yes, our modern computers are approximately universal, which is to say, the only thing that prevents any of them from calculating absolutely anything that is able to be calculated is a finite amount of memory. And so there are certain things for which our older computers might struggle to calculate simply because they can't store the information they need to store, or the processing might take too long on a slow processor. Presently, I enjoy playing with my virtual reality headset hooked up to a PC computer so I can play Microsoft Flight Simulator, the very latest version of Microsoft Flight Simulator. It's fantastic. You're there sitting in the cockpit and you can learn to fly different aircrafts to some degree of facility anyway, or at least pretend that you can. This kind of program, with its renderings of different cities around the world and its various aircraft to high accuracy, takes up a lot of memory. There's no way that back when The Fabric of Reality was written, 1997, that I could have used my computer then, a PC with a Pentium chip running at whatever it was back then, 300 megahertz or something like that, on a hard drive which had like 270 megabytes, something like that. There's no hope of that thing being able to render in reasonable time the environment of the virtual reality flight simulator. What would have happened is, Well, you'd probably get an image on the screen which was pretty grainy, but it would take, I don't know, an hour to draw a picture of the city that you were in before it moves on to the next frame, which would take another hour to do. And that's even ignoring the fact that you couldn't fit the program onto the hard drive anyway. You'd need a bigger hard drive. So although the processor could have in principle done the processing, in practice you need a faster processor if you want it to be more lifelike, if you want it to do the job that you really want done. So this is why we say computers are approximately universal. They can run out of memory. They can perform things a little bit too slowly. But this is not to say that, in principle, given enough time and enough memory, they could compute anything that's computable. These are general computers, universal computers, able to perform any task at all, unlike certain other computers which were special purpose computers. In a sense, the first weaving machines, looms, the Jacquard loom was a programmable device which was able to produce different kinds of weavings. Okay, so that's one thing. Babbage's original calculating machine could do arithmetic, but perhaps it was limited to that, although there are some claims that certain versions of this thing, the analytical engine, may have had universality. Again, limited in memory and certainly limited in speed. Recently, the Antikythera mechanism has been getting more and more attention. Even David Deutsch tweeted about it recently, a lecture from some years ago by Tony Freeth, who is one of the world experts on this particular early computer. It was a specialized computer that the Greeks were using over 2,000 years ago to do what? To calculate the position of astronomical bodies moving across the sky. Who knows what for precisely? Out of curiosity and interest. Also for navigation purposes, absolutely. Perhaps being able to figure out when to plant certain things, to predict events like, let's say, eclipses. Now, if you can predict an eclipse 2,000 or 2,500 years ago, down to the hour, it's going to appear to the average person that you have magical powers almost. So it could even be an interesting way to keep the citizenry in line. If they are persuaded that you have access to the gods and that you're telling them what the gods are telling you, like tomorrow at precisely 2 p.m. the sun will be blacked out by the moon, that's pretty impressive, right? Especially if no one else can do that. But you can do it because you've got the Antikythera mechanism. Now the Antikythera mechanism, this computer that the Greeks apparently used to make predictions of astronomical bodies, decades out to a precision of hours as to where the things were in the sky. This shows something deep about reality. It shows that you can have this one-to-one correspondence between a machine and stuff going on out there in the universe. There is this relationship between these two things. Now, in that case, the Antikythera mechanism, it did one thing. So far as we know, of course, more research could be done, and maybe it's more generalizable than that. Maybe it could quite easily be turned to doing stuff other than simply predicting the position of planets. Who knows? Who knows what we might find? But at the moment, that's what people think it was used for. Like many older computers of this sort, they're specialized to do one particular kind of task, one thing really well. And in this case, predict the position of planets. But it says something deep. It says that you can have self-similarity. Self-similarity between the gears of this mechanism and what's actually going on in the solar system. And in the same way, we can have our computers render environments which have a one-to-one correspondence between what's going on inside the internals of the computer and any environment that you want to render. And of course, then our universality goes further than that, and the one that fixates me quite often and the one that I get animated about is the one-to-one correspondence between the universality of our minds to explain the rest of physical reality and that physical reality itself. This model that exists between the mind here, inside the brain of a person, and, well, anything else that's out there. Indeed, everything else that's out there that is known to the person with the mind. The quantum computer is a new mode of computation. So it's not like there are additional tasks that it can do that the original Turing machine could not in principle do. It's just that the quantum computer can do some of those tasks much, much faster, more efficiently. David's going to get to what the technical meaning of efficiency is. One very hand-wavy way of talking about efficiency is that there might be certain tasks, let's say mathematical tasks, and to name one, the kind of task that he would talk about, which is, let's say you've got a number that you can easily write down on a piece of paper given enough time. Let's say you wanted to write down a number that was 2,000 digits long. Okay, it's going to take you a while to write it down, but you could do it, mate. You could probably get that task done in just a few minutes. Now, the difficulty is, let's find the factors, the prime factors of that number. It wouldn't matter if you had all of the computers in the world working for the entire age of the universe so far, 13.6 billion years, you wouldn't get the answer. Indeed, for a number of that size, it wouldn't matter if the entire universe was turned into a classical computer, where all of its internal workings were operating at the speed of light, you still wouldn't get an answer. However, for a task like that, if you had a reasonably modest quantum computer, you could get an answer in a few minutes. And so this is the difference in efficiency. Now, more precisely, as David explains it, the rough and ready definition, I suppose, or explanation of what efficiency is that for each digit you add to a really long number, does the amount of time taken to factorize this digit increase exponentially? Does it double, or does it just go up linearly? Does it just go up by a few more seconds? Well, if it doubles or it triples or it goes up in any way exponentially, then this is known as intractability. Your device might not be efficient for solving that particular problem. However, in the case of quantum computers, it is able to do these things efficiently. And of course, one thing on all this kind of stuff, talking about what a computer can in principle calculate or compute or simulate or model or whatever you like, is the requirement that you need a program to put into the computer to code. You have to give the computer instructions, but what instructions will you give it? What is the program you will write? It's no good saying, well, the computer can in principle plot the positions of planets across the sky if you don't know what they are. If you don't know what they are at the moment, in other words, the initial conditions, or what they will be tomorrow, or what they were yesterday, much less the laws that govern the motion of those planets, even if those laws are incorrect, but still enable you to predict tomorrow where they're going to be based upon where they are today, well, then the computer can't do it either. If you can't do it, if you can't in principle figure it out by pen and paper, at least partially, if you can't write down some set of predictive laws, if you don't know where the planets are today, if you don't know what the initial conditions are, the computer's not going to be able to do it for you. The whole point of the computer, the dumb computer, is to automate the process once you know how to do the process. But you only know how to do the process once you've used your intelligent, creative mind as a person to write down the algorithm, which can then be used as code to program a computer to give it a set of instructions. Now, I know that many in my audience are engaged in very much that work anyway, but for those not so familiar with the principles of computer science, this is what we mean by universality. It's not that the computer simply can do the thing, the computer will do the thing, that given enough hardware and enough memory and enough processing power, it will suddenly gain escape velocity, if you like, and be able to do all of these things. No, someone has to give it the instructions to do those things. And this is why the debate that arises often on Talkcast, in myself, between the people who understand what AGI is and those who think AGI is just AI, but with a greater repertoire of capacities, that the latter is so clearly an incorrect approach. Because the only way any AI, dumb AI that is presently used to do stuff for us, can do anything at all is because someone has programmed it with each of its capacities to play chess, to play AlphaGo, to translate languages, to be a chatbot of some kind or other, to be able to compose music perhaps. But until it is able to come up with its own tasks, until it is able to program itself with some new thing that hitherto no person had thought of before, including any human being, then we're not in the presence of an AGI. We're in the presence of a highly specialized intelligence of some kind, but not something that can ever add to its list of tasks or refuse to do one of the tasks that is given to it. Well, there we go. So yet again, we are brought back to that question here in a chapter on quantum computers. And I suppose one reason why it's important here with quantum computation is because people again and again will come up with the idea that AGI must require quantum computation in some way. We don't think that's the case. In particular, the reason we don't think it's the case is because quantum computation is a new kind of hardware. It's a new way of computing things. It's not a new bit of software. And when you're talking about AGI, you're talking about software, the set of instructions that enables some system to generate knowledge, to generate explanations. That's what a person is. But even if you had this fully functional universal quantum computer, again, what kind of program would you run on it? What is the set of instructions that you would feed into it so that it became a self-aware, fully functioning artificial general intelligence? We don't know. But if we do find that program, we have to present an argument as to why it wouldn't run on a classical computer efficiently and why we would need a quantum computer to do what it does efficiently. At the moment, there is no such theory, and we see no reason why it should be the case that we need to have a quantum computer to do this thing. But of course, no one knows. We're still in the realm of the unknown. Let's get back to quantum computers. And David writes, quote, "Quantum computation is more than just a faster, more miniaturized technology for implementing Turing machines. A quantum computer is a machine that uses uniquely quantum mechanical effects, especially interference, to perform wholly new types of computation that would be impossible, even in principle, on any Turing machine, and hence on any classical computer. Quantum computation is therefore nothing less than a distinctively new way of harnessing nature." End quote. So what David's not saying there is that the quantum computer can do more tasks of a kind. It can still compute the same, it still has the same repertoire as what a Turing machine has. It's just that it is a different way of computing things that no other computer could even in principle do, namely utilize interference in particular. These interference effects are something that are a feature of quantum physics, but not a feature of classical physics. The interference between particles as explained in the chapter called Shadows here in the Fabric of Reality, particles that can be observed and particles that in principle cannot be observed except by their effects on the particles that we do see. David goes on to say, quote, "Let me elaborate that claim. The earliest inventions for harnessing nature were tools powered by human muscles. They revolutionized our ancestors' situation, but they suffered from the limitation that they required continuous human attention and effort during every moment of their use. Subsequent technology overcame that limitation. Human beings managed to domesticate certain animals and plants, turning the biological adaptation in those organisms to human ends. Thus, the crops could grow and the guard dogs could watch even while their owners slept. Another new type of technology began when human beings went beyond merely exploiting existing adaptations and existing non-biological phenomena such as fire and created completely new adaptations in the world in the form of pottery, bricks, wheels, metal artifacts, and machines. To do this, they had to think about and understand the natural laws governing the world, including, as I have explained, not only its superficial aspects, but the underlying fabric of reality. There followed thousands of years of progress in this type of technology." End quote. I'm finishing the middle of the sentence there, but this is really important stuff. And again, hints at the beginning of infinity worldview here in the Fabric of Reality. What we're talking about here is the human capacity to gradually come to some understanding of the world, and in coming to understand the world, to improve their situation by creating technology which automates some of the hard work, turning their perspiration into an opportunity for doing other stuff and continuing to improve their lives. Let's look at food production. We have long known that if you grow this thing called wheat, then it can be used to produce this thing called flour, which when baked produces bread, which is a nutritious food for people. Okay. So what do you do if you've got basically no tools at all? Well, you take the wheat and you bash it with a rock and then you get the flour out of it. You're grinding the stuff, you're grinding the wheat into flour. And that's hard work, and you need a lot of flour to make a modest amount of bread. You mix it with water, you mix it with salt, you stick it in your oven and you cook it. And you bake it. Okay, I'm not teaching anyone anything here about how the baking of bread works. But how do we go from the situation where we're bashing the thing with rocks to something more automated? Well, you could take a big stone wheel. You could take a big stone wheel, but how do you drive the big stone wheel over the top of all of your wheat so that you don't have to do it? Well, if you're not going to push it, maybe you can get your animals to do it. Your domesticated animals can walk around and around in a circle, crushing the wheat between big stone wheels. That's great, that works, but still, you've got to feed the animals. And okay, that's going to cost you something because you're not eating those animals now. So there's some energy there. You know, they're probably going to be eating some of the wheat that you would otherwise be eating. All right. Maybe you can take a big water wheel and the water wheel will grind your flour and that will do the work for you. Or a windmill where the air is just doing the work for you. Moving air currents are doing the job of grinding the flour that you want, grinding the wheat into the flour. Okay, so now you're almost fully automated. You've got this windmill thing that is able to do the job. And of course, eventually what you have is you have some sort of combustion engine, steam engine, some sort of combustion engine anyway, where it's being driven by a fuel. You put fuel into the thing and it will just keep running so long as you keep replenishing the fuel, but the fuel is highly dense in energy, and so just a small amount of fuel can do heaps and heaps and heaps of work for you. So that's great. So now you're really on the way to automating things. And each time you automate something, and here we're just talking about the milling of wheat into flour, we're just talking about that, you've got all this time to do what? Time to think about the other problems in your life and find solutions to those and make things a heck of a lot better. This is what we should want to do. This is why, by the way, we shouldn't fear the AI. We should welcome it because it's automating stuff. And eventually we can automate all of our drudgery into stuff where we have time to reflect creatively on the work that we do. But each step of that process requires knowledge. To go from bashing wheat with rocks, very little knowledge required there, except that you need to know that there's actually nutrition inside of that crop that you grow, that wheat, to this wheel thing, and you figure out, this wheel, it actually has less friction and it requires less work to push the wheel than to lift up the rock. And well, if we can get something to push the wheel for us, we can learn that there's such a thing as domesticating animals. They can be trained. Then there we've learned something, and oh, look, the river is moving. The river can do some work for us. Let's turn the wheel into a water wheel. The wind can do the same thing. Maybe we can do that. Eventually you figure out, when you heat up something like water, it expands. This idea of water expanding and able to do work inside of a combustion engine in the form of a piston leads to this idea that we can actually have steam engines, machines. We have to understand something about how to improve the efficiency of those things with a limited amount of fuel. And so we begin to create our knowledge of mechanics and physics. So it's this whole problem-solving vision of the world and the ability to explain stuff that enables us, unlike any other creature that exists in the universe so far as we know, to improve our circumstance. This ability to create a model of the rest of physical reality, to explain the rest of physical reality through understanding physical reality. We're confronted with problems, we have to conjecture solutions. And this list of things that David has talked about here is this gradual ratcheting up of knowledge, this climbing a ladder, so to speak, where each rung of the ladder is only made possible by the fact that we have the rungs below it. We've made a little bit of progress previously, and we can build upon that to go a little bit higher. Conjecturing all our way, never getting to the top, never having finality, and perhaps discarding a particular ladder at times and constructing a whole new one that is able to take us to places that are far better than where we thought we were going to go in the first place. So let's just recap, because David says there that in understanding, coming to realize what these natural laws are that govern the world, the understanding of the fabric of reality, what happened then? There followed thousands of years of progress in this type of technology, harnessing some of the materials, forces and energies of physics. In the 20th century, information was added to this list when the invention of computers allowed complex information processing to be performed outside human brains. Quantum computation, which is now in its early infancy, is a distinct further step in this progression." End quote. Notice there as well this idea that a computer is simply processing some of the information outside of the brain in a sense. We could also say this about pen and paper, that sometimes we can't store all of the numbers that we need in our working memory, and so if we write them down, then this is a great way of calculating. Mathematicians have known this for a long time. This is one of the reasons writing systems were such a boon to mathematics as well, because very few of us, some people they can train their brains to just remember a 12-digit number and then remember another 6-digit number and multiply these two things together and to figure it out in their head. Many of us can't do that, but almost all of us can be trained to do that with pen and paper. So in a sense, some of the computation is being done outside. Yes, the processing is being done in here, the creative conjectures are going on inside of our minds. However, the memory is being stored on pieces of paper using pens. A computer is just the next step in that kind of thing where some of the processing is being done outside. Some of the memory is being left outside, being automated. And so although an astronomer can very well understand the laws that govern the motion of celestial bodies, how it is that the solar system works in the way that it does, why it is that Mars moves around the sun in the way that it does. And they could, in principle, write down the equations and then calculate through, given the conditions, given, where exactly Mars is today, what the mass of the sun is at the moment, and so on and so forth, how far Mars is from the sun. They could figure out where Mars is going to be 3 years from now. Sure, far better that, given that they already understand this stuff, to have the computer do it much, much faster than what they could ever possibly hope to do it with pen and paper, much less inside of their minds, calculating inside of their minds. They'd have no hope of doing that because, well, one reason is our memory is limited. Our working memory inside of our brains is limited in some way that we don't understand. Some people can improve their memories, by the way. See these people that can remember like phone books of information, literally, remember pi to thousands of decimal places, that kind of thing. So the brain is capable of doing these astonishing feats of memory, but also why, the primary function of a human brain is to solve particular problems and to solve the problems that you're interested in by conjecturing explanations and then refuting the bad explanations and making progress and all that stuff that we talk about. It's not mainly to demonstrate its amazing capacity to remember stuff, because one of the things that the brain has been able to figure out is how to outsource memory to paper, how to outsource memory to mobile phones, how to outsource memory to regular computers and that kind of thing, to libraries. We don't need to worry about trying to remember so much information. And indeed, in many situations, we don't even have to worry about how to process certain information as well. I don't need to worry about how to multiply huge numbers. I don't even need to know, although I do, the algorithm that is required in order to do it with pen and paper. Why? Because I know how to use a calculator. I know how to use my computer to do this thing. That's enough. I can do it far faster than anyone else who doesn't have access to those things. Okay, I can always outperform someone at a task which requires computation where they don't have a computer but I do. And in this day and age, I can find the answer to almost any question that a person would otherwise have really good knowledge of, but I don't have good knowledge of if you just give me access to Wikipedia and Wolfram Alpha and ChatGPT and the internet and Google and that kind of thing. In this circumstance that we have, people need to look for open problems, open, interesting problems, problems of interest to them. Yeah, sure, that does require building up some body of pre-existing knowledge, the background knowledge, so you know where the open problems are. You know what problems haven't yet been solved, but this is the fortunate position we now find ourselves in with respect to our ancestors who didn't know what was already known. They didn't know that someone on the other side of the world had already figured out the answer to their problem. If only they did, they could have collaborated and they could have worked on something new together rather than people simultaneously figuring out the same thing. I'm also not denigrating knowledge in anything that I say there. Of course not. My whole thing is knowledge. People should want to improve their own knowledge, if only to understand the structure of it, and so therefore how to improve the knowledge they do have in the areas that they wish to know about. But, I'm a big proponent of, yes, try and gain some general knowledge about everything, because everything is inherently interesting. Know a little bit of history, know a little bit of science, know a little bit of mathematics, know a little bit of politics, know a little bit about music. That's one area where I fall down. Know a little bit about languages. Again, I'm deficient in those areas. But try and learn a little bit about everything, because you will find that things are absolutely fascinating. As people get older, they tend to become fascinated by history. The older you get, the more fascinated by history you get. People can become fascinated by the classics, whether the classics in philosophy or the classics in literature and so on and so forth. I think that having a wide repertoire of approaches to these things is really important. So in saying that, well, the computer can do it all for you now. You can always Google stuff. You can always Wikipedia stuff. Yes, that's true. And that is increasingly more true. And it's just to say you don't have to remember a huge body of knowledge. That is not to say that a huge body of knowledge is not in and of itself of value, of interesting value to you, because it can spark your curiosity about things. It's not to say you need to remember every single date about every single important facet of World War II, let's say, in order to say you have an understanding of World War II. But you should have an understanding of World War II. It's useful to know that. Whether or not you know precisely the date and the time of when the landing on the beach of Normandy occurred, or why it was needed, well, that's another thing. But, people should have a good vision of what human knowledge is in our civilization at this given time. Broadly speaking, a nice overview of the landscape, so to speak, is of use to a citizen and of use to a person. Would I compel people to learn this? No, because I don't know specifically how deep you might want to dive on any one particular area. Is there a particular minimum you would want to prescribe? No, I don't think so. Again, I think it's all just about personal interest. But if you really do pursue knowledge, you'll just find that everything is just naturally of interest to some extent, and it'll be a different extent for everyone. And you don't need to mandate this, as I keep on saying. It just naturally is the case. You don't need to mandate it because people are naturally fascinated by it, which is my point about as people get older, they tend to get interested in history anyway, even if while they're going through school, it seems like one of the more boring subjects, given history teachers. We shouldn't put all the blame on the poor history teachers, or given the way the history books are structured and that kind of thing. But it simply is the case that history is not exactly one of the most popular subjects at school, kind of like science at times as well, although I think that's changing a little bit. Anyway, way off topic, that was a bit of a rant. Let's go back to the book. And David writes, quote, "Quantum computation, which is now in its early infancy, is a distinct further step in this progression. It will be the first technology that allows useful tasks to be performed in collaboration between parallel universes. A quantum computer would be capable of distributing components of a complex task among vast numbers of parallel universes and then sharing the results." End quote. Yes, and quite right. And this is where people begin to balk. Oh, well, how do you know these parallel universes exist and so on and so forth? Well, that's been dealt with earlier on in the book. That's the first thing to say about this. The second thing to say about this is, as David will come to, and as many people have observed before, if you want to factorize this huge number, and there is a way known that the quantum computer could do this in principle, Shor's algorithm, as we will come to, the factorizing of these huge numbers, which could not possibly be done by a computer in our universe. Even if the entire universe, all the matter in the universe, was repurposed to construct the ultimate classical computer, the fastest and biggest classical computer operating by the means that all the other computers that we have that exist that are not quantum operate by. And even if the switching speed of the transistors were moving at light speed, you still wouldn't be able to factorize certain numbers within some billions or perhaps even trillions of years. So if a quantum computer can do it, and it can do it, then where is the computation being performed? Where is it being done? It can't possibly just be done in this universe. After all, there's not enough computational resources in this universe to do that. But if it is done, and if it's done in a little box somewhere, in a laboratory somewhere, that feat is accomplished. It can't be accomplished just in that box. It must be that box and more. And what is the and more? Well, it's the other boxes in other universes working in concert with that particular box, interfering the mechanics that's going on, the quantum mechanics that's going on inside the internal workings of the box, sharing the problem of that computation, the computational task, with the other universes. That's how it works. That is the only way known that it could possibly do what it does. And it can possibly be done. That's the thing. Have we done it yet? No, because we haven't yet built a universal quantum computer capable of doing such a thing. But we will one day. Problems are soluble. Perhaps it's taking a little longer than what we hoped, but, you know, so too is interstellar travel. There's a lot of things in flying cars, as people say. Sometimes we make huge advances. Information technology, smartphones. No one really saw smartphones on the horizon. We sometimes get the gift we didn't even ask for and didn't expect. And sometimes we don't. We just have to keep persevering and making the progress. Let's keep going. David writes, quote, "I have already mentioned the significance of computational universality. The fact that a single physically possible computer can, given enough time and memory, perform any computation that any other physically possible computer can perform. The laws of physics, as we currently know them, do admit computational universality. However, to be at all useful or significant in the overall scheme of things, universality, as I have defined it up to now, is not sufficient. It merely means that the universal computer can eventually do what any other computer can do. In other words, given enough time, it is universal. But what if it is not given enough time? Imagine a universal computer that could only execute one computational step in the whole lifetime of the universe. Would its universality still be a profound property of reality? Presumably not. To put that more generally, one can criticize this narrow notion of universality because it classifies a task as being in a computer's repertoire regardless of the physical resources that the computer would expend in performing the task. Thus, for instance, we have considered a virtual reality user who was prepared to go into a suspended animation for billions of years while the computer calculates what to show next. In discussing the ultimate limits of virtual reality, that is the appropriate attitude for us to take. But when we are considering the usefulness of virtual reality, or what is even more important, the fundamental role that it plays in the fabric of reality, we must be more discriminating. Evolution would never have got off the ground if the task of rendering certain properties of the earliest, simplest habitats had not been tractable, that is, computable in a reasonable time, using readily available molecules as computers. Likewise, science and technology would never have got off the ground if designing a stone tool had required 1,000 years of thinking. End quote. Okay, so what is David saying there in talking about this idea of universality, computational universality, as being a fundamental feature of the fabric of reality? Why should it be a fundamental thing? Well, because the laws of physics didn't have to be such that we could build devices which could be used to compute, calculate, predict, model the rest of physical reality, to help us to gain an understanding of the very laws themselves that enable everything that happens to happen, everything possible that can possibly happen, and rule out the things that can't possibly happen. The laws of physics are such that we can have these devices called computers that are universal, that can have within them the capacity to simulate any physically possible process. That's a remarkable feature of the fabric of reality as it is, given by the laws of physics as we understand them. So the fact that it is possible for these devices to be built, much less that we have built them, certainly in the case of classical computers, is a fundamental feature of the fabric of reality. David Deutsch has made the point on other occasions that many people are somehow more fascinated by the idea of the simulation hypothesis, this idea that the entire universe itself, reality, physical reality, actually is running on a computer somewhere, that is not as astonishing a claim or as significant a claim as the fact that computers are possible in the first place, that universal computers are able to be built within our universe and then used to model anything else, and therefore help us to solve problems, come to a deeper understanding of everything else as well. And just to discard that simulation hypothesis for a minute anyway, it doesn't solve anything. It never solves anything to say that this reality that we occupy, this apparent physical reality, is running on a computer somewhere or other. It's precisely the same problem as saying, well, to solve the mystery of existence, we just postulate this omnipotent God that has created it all. Well, that doesn't solve anything. In particular, it doesn't solve the problem of who created God. And if you say, well, God needs no creator, you're just moving the problem elsewhere. You could just say all of physical reality needs no creator. It's the same answer. But the problem with the simulation hypothesis is that you say, well, if this physical reality we occupy isn't genuine physical reality, it's a simulated one, and we all exist inside the simulator, many of us want to ask the question, where is the computer on which the simulation is running? And what laws of physics does it operate by? Are the laws of physics in the universe where the computer is running this simulation of this physical reality, are those laws of physics different? And is that inside of another simulation? And so on, with different laws of physics, so on ad infinitum. This isn't solving anything. This is proliferating worse problems without us making any progress. This is philosophy for philosophy's sake, not solving an actual problem, but rather conjecturing problems into existence whose solutions we do not have, and we cannot hope to have, given any understanding of the physical world in which we find ourselves, at the moment anyway. It is, as I like to say, philosophy purely in the abstract. It's not connected to the physical world, which is, philosophy at its best is able to do that in some way, shape or form. The philosophy is able to connect to our physical world. It doesn't mean it has to be testable in the physical world, that's science. But it has to have some connection to us. If it has no connection to us, even in principle, then it's uninteresting by that metric. No one can it can't affect anyone, so it can't be interesting. What are the physical laws governing the universe 10 rooms over, running a simulation of a world that is kind of like ours? Well, we're not there and we're never going to be part of that, and apparently whatever the laws are that are governing this universe prohibit us from even getting outside of this universe. And so postulating the existence of these other logically possible universes which are running computers which themselves contain civilizations and worlds and whatever else is purely abstract thinking. It's with no connection. And what I say is it's inherently uninteresting in the sense that it doesn't possibly solve any problems here that could affect people. That aside, David has talked about here this notion that happily the laws of physics are such that we can make progress in reasonable time. It is possible to design stuff like stone tools, and they allow us to make progress, which leads to more progress and opens up new problems, which themselves provide solutions which enable more rapid progress still. So the laws of physics are such that this is able to be done by creative people. He goes on to say, quote, "Moreover, what was true at the beginning has remained an absolute condition for progress at every step. Computational universality would not be much use to genes, no matter how much knowledge they contained, if rendering their organism were an intractable task. Say, if one reproductive cycle took billions of years. Thus, the fact that there are complex organisms and that there has been a succession of gradually improving inventions and scientific theories, such as Galilean mechanics, Newtonian mechanics, Einsteinian mechanics, quantum mechanics, etc., tells us something more about what sort of computational universality exists in nature. It tells us that the actual laws of physics are, thus far at least, capable of being successively approximated by theories that give ever better explanations and predictions, and that the task of discovering each theory given the previous one has been computationally tractable, given the previously known laws and the previously available technology. The fabric of reality must be, as it were, layered for easy access." End quote. That's fantastic. This gives the idea of emergence to some extent, that you have this emergent simplicity. So far as we know, at the moment, we have this theory, quantum theory and quantum mechanics, which explains how it is that motion occurs between particles. Everything's made out of particles in the universe, so therefore it is a universal theory of how stuff happens generally. However, there are these emergent laws, these laws that seem to apply at certain scales. There's this layered aspect to reality, so that Newtonian mechanics works to a good approximation for low velocity and big things, but not too big, not so big as, whole galaxies or stars or something like that, where the gravitational effects then have effects that normally aren't noticed at smaller scales. There's emergent simplicity, where biological organisms and indeed whole ecosystems appear to obey laws which are not easily derived from the laws of quantum theory. There is this emergent simplicity. As we like to say here, there's no point talking about the causes and the reasons why, the explanations for what happened during the Second World War in terms of physical laws, the laws of dynamics, what's going on at the level of quantum theory with the particles. No, you want an explanation in terms of tyranny and liberty, things like force and bombs and invasion and leaders and Adolf Hitler and Winston Churchill. This is the level of analysis that you want in order to come to an understanding of what's going on, to generate an explanation of what's going on. Being able to, in principle, predict the motion of particles is not able to get you one jot closer to understanding what's going on in the overwhelming majority of phenomena that happen amongst humans in their civilization, or even the universe as a whole. It will get you a lot in terms of understanding how particles behave. Of course, absolutely, everything's made out of particles, so it gives you some insight into the behavior of the universe as a whole. But at one particular level, one strata, if you like, of knowledge, but it's not the only strata of knowledge. The world is layered, as David says there. There are these layers to coming to understand the world, and we can have more and more, we can have better and better approximations to things as well, which introduces this notion of improving computation over time. Our first computers were these special purpose computers. Okay, we mentioned the Antikythera mechanism earlier, this Greek computer over 2,000 years old that was found. It was exquisitely special purpose so far as we know. It was designed in order to predict the motion of heavenly bodies, okay, so to know where the moon was going to be any day of the week, any hour of the day many years in advance. So it could predict eclipses, it could predict where the sun was going to appear on the sky, it could predict where the planets were going to be with relation to the constellations that they appeared in the zodiac. It was special purpose. Why? Because the laws of physics as understood at that time were just purely mechanical, classical laws. In Greek times, Aristotle's physics of some sort or other, which kind of resembled what Galileo kind of came to know. And of course, you had Babbage's idea of a computer of a kind resting upon Newtonian laws. And still, through to Turing, Turing's idea of computation still rested upon some notion of classical physics as well. But we had an improvement in computation. As the improvement in our understanding of physics progressed, then we continued to have improvements in technology as well, until we're at the point today where we have this notion of quantum computation unifying Turing's idea about the computer, about a universal computer, with quantum computation, recognizing that whatever the computer is made out of, it's made out of matter, which obeys quantum laws of physics. David Deutsch unites these two things into this field of quantum computation. Is it the final step in computation? One would imagine not, because once you have a unification in some way, shape or form of quantum stuff and gravity, then you have perhaps a new mode of computation. I've already imagined the fantasy idea of a computer so large that it was built out of all the matter in the universe. Can you imagine such a computer? If you can, if you could imagine a computer the size of a galaxy, okay, there are many galaxies throughout the universe, so one galaxy is tiny, minuscule compared to the volume of the universe. If you could, in some distant future, take all of the matter within a galaxy and turn it into a computer, you'd have some interesting effects going on, because if in theory that could be done and it could operate at the speed of light, well, aside from the fact it would take a long time for memory in one part of the computer to ever communicate with memory in another part of the computer, you'd also have gravitational effects with something like that. And if you have gravitational effects with something like that, because it's simply so huge, it is warping the background space and time, and it's affecting the trajectories of whatever the thing is made out of. If it's transmitting photons from one place to another, those photons are now following curved paths. And so the computation, presumably, would be operating via a different mode, some sort of quantum gravity computer. Who knows? We're thinking in terms of science fiction here. But my point is, there would be a mode of computation beyond the quantum computer as we understand it now. It would involve also taking account of the effects of gravity. Now, what's beyond that? Who knows? Who knows what constructor theory would reveal in the distant future as well. As our theories improve, our predictions about the motions of particles become more precise, and our capacity to take advantage of such predictions in order to generate technology of high precision and high accuracy improves in lockstep as well. All of this rests upon coming to a deeper understanding of reality, creating the knowledge of how it is that all this stuff works. David goes on to say, quote, "Likewise, if we think of evolution itself as a computation, it tells us that there have been sufficiently many viable organisms, coded for by DNA, to allow better adapted ones to be computed, i.e. to evolve, using the resources provided by their worse adapted predecessors. So we can infer that the laws of physics, in addition to mandating their own comprehensibility through the Turing principle, ensure that the corresponding evolutionary processes, such as life and thought, are neither too time-consuming nor require too many resources of any other kind to occur in reality," end quote. So this is this beautiful idea of self-similarity, again, that we've got here, that the laws of physics mandate their own comprehensibility through the Turing principle, elevating the Turing principle beyond regular physical laws, that any physical law that is now discovered needs to comport to this idea of the Turing principle, because the laws of physics are themselves computable. Why? Because that is proven. That is one of the things that is proved by David Deutsch's proof. That if the world is quantum, you can build these things called quantum computers. The quantum computers can simulate any physically possible process. And the physically possible processes are those ones which are governed by the laws of physics. So you can model in your computer things that obey physical laws, because you can model matter, and matter is the stuff that obeys physical laws. Would the discovery of a quantum gravity computer change any of this? Well, presumably yes, but would it radically overturn all of the possibilities that quantum computers open up for us? No, I imagine it would only widen the repertoire. It would make things even more universal. There are degrees of universality. You could have a computer that is more universal, that could model all the effects of gravity, which presumably there may be something that a presently existing quantum computer might not be able to do, I don't know, this is beyond me. Perhaps a computer that can take advantage of gravitational waves in some way, shape or form might be able to do computations that are different to the repertoire of computations that can be done by a regular quantum computer. Again, I could be wrong about that, but the thing is, quantum physics is not a theory of gravity, which includes things like gravitational waves. David goes on to say, quote, "So the laws of physics not only permit, or as I have argued, require, the existence of life and thought, they require them to be, in some appropriate sense, efficient. To express this crucial property of reality, modern analyses of universality usually postulate computers that are universal in an even stronger sense than the Turing principle would on the face of it require. Not only are universal virtual reality generators possible, it is possible to build them so they do not require impractically large resources to render simple aspects of reality. From now on, when I refer to universality, I shall mean it in this sense, unless otherwise stated." Let's just reflect a little on what is said there. So this is in line with David Deutsch's more recent philosophy as well about constructor theory, the possible and the impossible, but also this notion that nothing happens randomly. The world is not probabilistic. What happens, happens as a matter of being determined by the laws of physics. What happens is determined. So therefore, when he says, the laws of physics not only permit, but as I have argued, require the existence of life and thought. Now, why would he say that? Why isn't it just the fact that life and thought could arise? It doesn't necessarily. Well, the fact that it has arisen means that it's determined to have risen, right? If you run the multiverse experiment again, then you get the multiverse. You get all the physically possible universes. This one that we occupy, we look back and we see a series of events that happens that are not random. It's an actual history that has led to us. There are reasons why life has arisen. There are reasons why life which is able to think has arisen. We can provide an explanation. It's not like a vanishingly small sliver of the multiverse. No, this is an important branch of the multiverse. One would imagine many branches of the multiverse. And when life arises, then this is a form of knowledge instantiation in the universe. Knowledge is resistant information, information that can survive the slings and arrows that the cosmos throws at it. Once you get people, you get these creative thinkers, then you have explanatory knowledge, which is the most resistant entity in the universe, as Chiara Marletto has put it in her books, and as David Deutsch no doubt would agree, the most powerful force, effectively, force speaking metaphorically, in the universe, able to construct around it a shield, if you like, against the otherwise inhospitable, implacably dark void that is the rest of the universe. And it will go on replicating, constructing, building itself, designing new structures, coming to a deeper understanding of the reality that it occupies, and shaping that reality around us. So this is the sense in which the laws of physics require the existence of life and thought, simply because we are here and it's not a chance random event. I know that people normally like to talk in this way, especially when it comes to random mutation and selection. Yes, but there's only a finite mutations that can happen. Some of them are selected for. Now, why? Well, the universe selects things that are going to succeed in a given universe. We are one such. Thought is one such thing. So this is why this is yet another reason why this worldview is profound. Things are determined to exist. They're not just random, spontaneously generated stuff. It's not a roll of the dice. It's not probabilistic. Stuff happens. And some branches of the multiverse, yeah, life didn't arise, thought didn't arise, but that's not what we're talking about. We're talking about arising in the multiverse, not in every single universe, in the multiverse, in physical reality, which it has. Why? Because it's determined to have done so. Why? Because that's what the laws of quantum theory say. A fantastic idea, this one. Let's keep going, and we'll finish up shortly, because already I've spoken too long in just this first episode. So I was planning on perhaps only doing 2 episodes, but I think we're going to go to 3 somehow when it comes to this quantum computation chapter here in the Fabric of Reality. David goes on to say, quote, "Just how efficiently can given aspects of reality be rendered? What computations, in other words, are practicable in a given time and under a given budget? This is the basic question of computational complexity theory, which, as I have said, is the study of the resources that are required to perform given computational tasks. complexity theory has not yet been sufficiently well integrated with physics to give many quantitative answers. However, it has made a fair amount of headway in defining a useful rough and ready distinction between tractable and intractable computational tasks. The general approach is best illustrated by an example. Consider the task of multiplying together two rather large numbers, say 4,220,851 and 2,594,209. Many of us remember the method we learned in childhood for performing such multiplications. It involves multiplying each digit of one number in turn by the digit of the other number in turn, while shifting and adding the results in a standard way to give the final answer. In other words, pausing there my reflection, in other words, this idea of adding a zero, adding two zeros as a placeholder so that you can do this computation. Everyone learns this method. Now, I'm not going to read the entirety of this section of the chapter. I'll just explain it in my own words. So this idea that you have this algorithm that people learn of how to multiply two numbers together. If you have to multiply 54 times 92, okay, you know how to do that, and someone teaches you how to do that. Then if you add a third digit, if you say instead of 54, we're going to do 542, and we're going to multiply that by 923, it's not that much harder. It takes you a little bit longer. It doesn't take you double the amount of time, however. It doesn't become intractable. And if you can program your computer to multiply two-digit numbers together, then the multiplying two three-digit numbers together is not that much harder. It's not going to double the amount of time. It's going to add a little bit more time onto the calculation. It's not going to double it or triple it or anything like that. However, the reverse operation does become intractable. If you have to find the factors of a particular number, and when I say factors, I should say prime factors of a number, it can be a heck of a lot harder. You know, take 10 times 10. People can just automatically say, well, it's 100. Okay, they learn that off by heart. And if you don't know it off by heart, you can figure it out pretty quickly. But if I say to you, what are the prime factors of 100, then it's then that people, take a little bit longer generally to do this particular calculation. It just takes longer. Having just told you 10 times 10, you might immediately leap to, well, 10 is 5 times 2, and the other 10 is 5 times 2, so you've got 5 times 2 times 5 times 2. Okay, so you've got 5 times 5, which is 5 squared, times 2 squared. Okay, and that's the prime factorization. They're the prime factors of 100. 2 squared times 5 squared gives you 100. You can do this for any number. Every number can be decomposed into its prime factors. It's a fun thing for kids to learn to do, by the way. If you're interested in teaching kids about arithmetic, it actually turns out to be a fun kind of challenge. This is intractable, however. As soon as you start adding digits to your number, things begin to spiral out of control. For any two-digit number, okay, it's reasonably easy to do this kind of thing. Let's take the number that's one less than 100, 99. Okay, so let's find the prime factors of that. Well, now you've got 9 times 11. All right, 9's not a prime number, but 11 is a prime number. So what are the factors of 9? Well, 3 squared. So you've got 3 squared times 11. There you go. That's the prime factorization of 99. But now, that's a two-digit number, three-digit number, 100. So let's start adding, digits. Pick any old four-digit number that you like, within reason. 2,525. Okay, 2,525, it ends in a 5, therefore it's divisible by 5, so divide it by 5. You can already see that things are going to get a little bit more tricky here. Each time you add a digit, 5-digit long number, 6-digit long number, things become harder to decompose into their prime factors. Now, there's even a special case of this. What if you take two really huge prime numbers that are known to be prime, and you multiply them together to get an unbelievably huge number, which you know only has two factors, namely the two prime numbers that you've multiplied together. There are no two other numbers in the universe that exist in reality, physical or abstract, that can be multiplied together to give you that particular number. So these two huge prime numbers, when multiplied together, give you a third even bigger number. Now, if you take that third even bigger number and give that as a problem to someone or a computer somewhere to try and figure out the prime decomposition of, no hope. No hope, because you just don't know where to begin. The only way of doing this, the only way of doing prime factorization is to run through in sequence, one at a time, all the prime numbers that could possibly be factors. So you start with 2, you see if the number is divisible by 2. If it is, hey, happy days. But if it's not, well, you move on to 3. Then from 3, you go to 5 and 7, you know the prime numbers. You're dividing your big number by prime numbers. Now, if the only two prime numbers that can be multiplied together, the only two factors, numbers are already huge numbers, it's going to take you forever to get through. And when I say forever, I mean like almost literally forever, okay? Your lifetime, the universe's lifetime, okay? This is the basis of certain kinds of cryptographic security. Okay, so that's Brett Hall's explanation of this. Let's go to the book and we'll see what David Deutsch has to say about some of this kind of stuff. He comes back to it towards the end, by the way. And I'll just pick it up where he defines a little bit more precisely what tractability means. So the fact that you can multiply two numbers together, that's a tractable problem, but decomposing them into their prime factors is an intractable problem. Why? He says, quote, "What counts for tractability according to the standard definitions is not the actual time taken to multiply a particular pair of numbers, but the fact that the time does not increase too sharply when we apply the same method to ever larger numbers. Perhaps surprisingly, this rather indirect way of defining tractability works very well in practice for many, though not all, important classes of computational tasks. For example, with multiplication, we can easily see that the standard method can be used to multiply numbers that are, say, about 10 times as large with very little extra work. Suppose for the sake of argument that each elementary multiplication of one digit by another takes a certain computer 1 microsecond, including the time taken to perform the additions, shifts and other operations that follow each elementary multiplication. When we are multiplying two 7-digit numbers, then the total time, David provides an example, the total time required for the multiplication, if the operations are performed sequentially, will be 7 times 7 or 49 microseconds. For inputs roughly 10 times as large as these, which would have 8 digits each, the time required to multiply them would be 64 microseconds, an increase of only 31%. End quote. Okay, so we've got this increase of 31% if we just add an extra digit onto our 7-digit numbers, so that now we're multiplying two 8-digit numbers together, which is tractable, okay? So the time takes a little bit longer, but it's not a massive increase. Okay, so let's take that same concept that we've got this hypothetical computer that can multiply these numbers together. David goes on to say about this. We've got two 125-digit numbers. Now, why would you want a 125-digit number? Because of cryptography. Trying to keep information secure, especially on the internet, requires this kind of multiplication and division to go on. Okay, so let's say you're interested in multiplying two 125-digit numbers. What David says about this. Quote, "Products of prime numbers of 125 digits or so are of great interest to cryptographers. Our hypothetical machine could multiply two such prime numbers together, making a 250-digit product in just over a hundredth of a second. In 1 second, it could multiply two 1,000-digit numbers, and real computers available today can easily improve upon those timings. Only a few researchers in esoteric branches of pure mathematics are interested in performing such incomprehensibly vast multiplications. Yet we see that even they have no reason to regard multiplication as intractable. By contrast, factorization, essentially the reverse of multiplication, seems much more difficult." End quote. And I've already explained what the process of factorization is. You take some large number and you figure out what the factors are, what numbers you would multiply together to get that number. And when we talk about factorization, we're really talking about what are the prime numbers that can be multiplied together to give that final number. And just remember, maths revision lesson for anyone who's interested in this stuff, for people who might have forgotten, prime numbers are like the atoms of numbers. They are the atomic numbers, if you like. Every other number can be made up of a combination, by multiplying them, just by separating them by multiplication signs, of prime numbers. Integers, I should say, of course, integers. So again, the number 10 is made up of the prime factors 2 and 5, and there are no other prime factors. Okay, the number 12 is made up of the prime factors of 3 times 2 squared. Okay, then there are no other different ways of multiplying numbers together to get 12, prime numbers together to get 12. This is what we're after. But as the numbers get big, it becomes very, very hard to figure out what the prime numbers are that make that number up. Let's say we take, and David uses this example, let's say we took a prime number, some number we know is prime. It's a big number. 4,220,851, there's one, and another number, 2,594,209. Both of these are prime numbers. Now we're going to multiply them together. We're going to get the answer of 10,949,769,651,859. Okay, so there we have this huge number, this 10 trillion number. What are its factors? Well, we know because we've just multiplied them together. But for anyone who doesn't know, good luck. Somehow they have to work through the list of prime numbers Starting at 2, going to 3, 5, 7, 11, and so on, until they get to the number 4,220,851. They will have found that prime number. And then once they find that prime number, well, actually, they would have found the other one first, right? If they're going sequential, they would have found 2,594,209. Now, how many prime numbers are between 2 and that number there? I don't know. You could easily look that one up, but presumably a computer could do this. But you don't have to imagine a much bigger prime number than this, where the computer will take too long to do this, David goes on to say. In fact, in explaining what I've just explained, but let me go into it. But after saying there is no easy method of doing this, the method is just what I've said. Quote, "The most obvious method of factorization is to divide the input number by all possible factors, starting with 2 and continuing with every odd number until one of them divides the input exactly. At least one of the factors, assuming the input is not a prime, can be no larger than the input's square root. And that provides an estimate of how long the method might take. In the case we are considering, our computer would find the smaller one of the two factors, 2,594,209, in just over a second. However, key point, however, an input 10 times as large would have a square root that was about 3 times as large, so factoring it by this method would take up to 3 times as long. In other words, adding one digit to the input would now triple the running time. Adding another would triple it again, and so on. So the running time would increase in geometric proportion, that is exponentially, with the number of digits in the number we are factoring. Factorizing a number with 25-digit factors by this method would occupy all the computers on Earth for centuries. The method can be improved upon, but all methods of factorization currently in use have this exponential increase property. The largest number that has been factorized in anger, as it were, a number whose factors were secretly chosen by mathematicians in order to present a challenge to other mathematicians, had 129 digits. The factorization was achieved after an appeal on the internet by a global cooperative effort involving thousands of computers. The computer scientist Donald Knuth has estimated that the factorization of a 250-digit number, using the most efficient known methods, would take over 1 million years on a network of 1 million computers. Such things are difficult to estimate. But even if Knuth is being too pessimistic, one need only consider numbers with a few more digits, and the task will be many times harder. That is what we mean by saying that the factorization of large numbers is intractable. All this is a far cry from multiplication, where, as we have seen, the task of multiplying a pair of 250-digit numbers is a triviality on anyone's home computer. No one can even conceive of how one might factorize 1,000-digit numbers or million-digit numbers. At least no one could conceive of it until recently. End quote. That's where I'll end for today, because we know now the answer. We know that quantum computation comes to the rescue of this. Now, we can't do it yet. We don't have a universal quantum computer that can actually do this kind of factorization. We know it can be done in principle. We just can't yet do it in practice. And next time we're going to talk more about that, and we're going to talk about the distinction between quantum events, which contain uncertainty, and classical events, which also can contain uncertainty. The idea of classical uncertainty leads to complexity theory and leads to this notion of chaos theory, which, as David says in his in the chapter here about to come up, was fashionable at the time when the Fabric of Reality was being written. I remember that quite clearly as well, that when I bought the Fabric of Reality, other books on the shelves were quite a number about complexity theory and chaos theory. The Mind of God by Paul Davies contained stuff about chaos theory. There was I forget the name of the book now, but there was a book there about nonlinear differential equations, and I ended up taking a subject in university about nonlinear differential equations because I became absolutely fascinated by this idea that you could have these systems which became chaotic. They were perfectly deterministic, but were exquisitely sensitive to the initial conditions. Now, as David will explain, you don't get these chaotic effects in reality. This butterfly effect is one that is talked about most often. The butterfly flaps its wings in Mexico, and then there's a hurricane produced on the other side of the world. You know, there's a cyclone in Brisbane or something like that. Well, this doesn't happen in reality. That's chaos theory, right? If the world was governed by classical physics, that could happen. Why could that happen? The reason why it could happen under classical physics is because the air being disturbed by the butterfly will never decay exactly to zero in classical physics, much like under Newtonian mechanics, classical gravity, let's say. There's never a point at which the gravitational effect falls to zero. It just doesn't happen. And so too with the butterfly flapping its wings. It moves a little bit of air around in its local vicinity, and then a little bit further away, the disturbance of the air is smaller, and a little bit further away still, the disturbance of the air is smaller, but it never gets to zero. It just decays to smaller and smaller and smaller amounts, leading to the possibility of chaotic effects, because that small amount can be just the right amount of kick to cause something else to amplify. But under quantum theory, effects can and do decay to zero. The electromagnetic theory of light that requires us, or that asks of us to conceive of light, for example, as being a wave, also would imply that light never gets to zero intensity, that if you shine a light, you can continue to turn it down ever dimmer and dimmer and dimmer, and you never get to a minimum amount of dimness. Quantum theory says quite the opposite. You do. You get down to these individual photons of light. You can get to a smallest possible amount, and the next step down is zero. Under classical physics, there is no smallest possible amount. And so you just decay ever more closely, asymptotically to zero. This is not quantum theory, however. So the butterfly effect doesn't exist under quantum theory. That same kind of butterfly effect does not exist under quantum theory, precisely because the disturbance of the air can decay to zero. The amount of energy can reach a minimum below which you just don't have any effects at all. Okay, so that's what we can look forward to next time, a discussion of this kind of a thing. But we've set the scene now for why it is that quantum computation can be a revolution in some areas. For example, in this idea of cryptography, not to mention all the other ways in which the real world consists of actual quantum objects like molecules, which at the moment cannot be accurately modeled by any computer, any classical computer, but could be modeled by a quantum computer. But until next time, bye-bye.